Is this aromatic, anti-aromatic, or non-aromatic? Right, it's non-aromatic, anti-aromatic. Yeah, it's anti. We can get 4 pi electrons out of that. Oh, let me come up with something a little different. All right, well, I'm gonna just end. We can do some more examples in a little bit. Here's where we ended Monday. We can deduce from this slide that these protons are acidic. So we take something that's non-aromatic and it becomes aromatic, and then these electrons are delocalized. And that's like our common theme for what can stabilize a base. And then some little strange thing with carboanion being sp2 hybridized. So I teach students that carbocations are sp2 hybridized, and we have the right number of electrons for Huckel's rule. And so here's our T-butoxide base. Once that proton comes off, this becomes very sp2-ish, and we get an aromatic anion. And it's not quite as stable as benzene, but it can react with electrophiles. So here we have an alcohol, and if we protonate it, we can make a good leaving group. And here would be a secondary carbocation, and this says this is not formed. So these things over here are non-aromatic, and as soon as you do this, you get something that would be predicted to be anti-aromatic, and we don't observe this. Go in the lab and try and do this, you're gonna have a hard time. So here's our cyclopentadiol anion, 1, 2, 4, 6. So this thing is aromatic. Now in the previous slide where we had the alcohol and protonated it and got it to leave, this would be the corresponding cation. And we could draw resonance structures and maybe assume it's real stable because of how the positive charge is delocalized. But that would be misleading. We'd want to say this thing is anti-aromatic according to the rules we've learned. I was trying to draw a 7-membered ring just a while ago, and you saw that I gave up. So, is this aromatic? No, we have an sp3. We're kind of set up 2, 4, 6, got the right number of electrons there. Now we protonate that OH, it leaves. Now we have a carbocation. Carbocations are sp3 hybrid for the most part. We have a nice flat planar ring, and I'd probably argue that this is aromatic. Commonly known. Nobody knows this except chemistry teachers or organic students. So this thing is aromatic. If I come down here and if we form the anion somehow, 2, 4, 6, 8, what does that tell us? 8 electrons. Well, let's review. Can I get 8 out of this? I can get 2, I can get 6, or I can get 10. Can I get 8 electrons here? Yeah, make that 2. So this thing might have to figure out is anti-aromatic. Now here's this thing that looked like a tub. And I said this was misleading. So this thing is not planar. So we don't have to apply Huckel's rule. We already know it's not at all. So here's some potassium metal. And somehow we're going to pull off some hydrogens. Probably some H2 over here. And now what do we have? 2, 4, 6, 8, 10 pi electrons. And we're told it's aromatic. Dianion. So this thing is non-aromatic. This thing is aromatic. Which of the following compound is an aromatic compound? Yeah, this one is aromatic. Is this one aromatic? No, there's that sp3. Oh. Can't delocalize anything. This thing we say, this is a typo. Pyridine, kind of a nasty compound. It'll, if you get exposed to a lot of it, it'll make you sterile if you're a guy. And the question might be, is this thing aromatic? What's going on? This drawing kind of makes it look so. 2, 4, 6. Do I count these or not count these? We have to assume these are stuck in a sp2 hybridized orbital, and we have a leftover p p orbital, and it says the two non-bonding electrons on nitrogen are stuck in sp2 orbital, and they do not interact with this pi system. So we don't count them. Pyridine is aromatic. Now it's also a base. So here's some water. Here water protonated it, and we call those basic electrons. And it's still aromatic. It's aromatic here, aromatic there. Here's pyrrole. Now I don't like this section. Sometimes I just skip it because of what I teach students in general chemistry. Here's what I teach students in general chemistry. In general chemistry, I teach hybridization this way. Want to know the hybridization of this atom? Count electron domains. There's 4. Got to have 4 hybrid orbitals. 1, 2, 3, 4. Same thing here with this oxygen. How do I get an sp2 hybridized oxygen? And I count 1, 2, 3 electron domains. So when I get to this point of the book, I kind of like to go, well, 1, 2, 3, 4 electron domains. I'm going to say that this atom is sp3 hybridized, but Wade says no. So I guess for right now we can say, well, if we're dealing with a ring and there's a double bond close by, we just get rid of what we learned in Gen Chem. And according to this picture, 2, 4, 6. So this pyrrole is aromatic. The pyrrole nitrogen atom is sp2 hybridized. I'm gonna have to just take their word. But the way I teach it in Gen Chem, I'd argue that that looks pretty sp3 to me. So we just have to accept that and move on with a lone pair of electrons in the leftover p orbital. This p orbital overlaps with the p orbitals of the carbon atom to form a continuous ring, which makes it aromatic. And we can use Huckel's rule, n equals 1. 4 times 1 is 4 plus 2 more is 6. We get 6 there. So once again, hard for me to swallow that, but I'm going to accept it. Now what might be better is you've probably read where, well, we'll just have to believe these electrons are, like it says, in a unoccupied p orbital. Now if we protonate this, now we have these 4 domains and we say it's sp3. So the protonated is non-aromatic, while the non-protonated is aromatic. So to compare and contrast that with pyridine, pyridine is aromatic regardless of whether it's protonated or not. Pyrrole is aromatic when it's not protonated, and non-aromatic when it is protonated. Once we protonate it, it becomes non-aromatic. So here are some other heterocyclic molecules. So they count these, but not those. They count this one, but not that one. Count that one, count that one. So some things that are like benzene are polynuclear aromatic hydrocarbons, where we can have multiple rings like this. And when it says only one Kukulay structure is shown, meaning you can move all those double bonds around. So it's nice just to use the circles, perhaps. Gen Chem, you might have found the molar mass of naphthalene. You might have noticed it smells like mothballs. Is naphthalene aromatic? Must be, it's in this chapter. Well, I don't know. Everything is sp3 hybridized. 2, 4, 6, 8, 10. There you go. 10 follows Huckel's rule. N being equal to 2. 2 times 4 is 8. 2 more. 10 electrons. Naphthalene is the simplest fused aromatic hydrocarbon. Here's pyrene. Here's benzo-A-pyrene. And dibenzopyrene. Is this thing aromatic? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I'm going to just say it is. Why don't I be a math major geek? What did I get? 24 electrons? What's N? 5 times 4 is 20, plus 2, that'd be 22. 6, 24, 20. Well, I'm choking on this at the moment. So let me tell you, this thing is a killer. You don't want to be exposed to it. A lot of these are formed in exhaust, and when things burn, formed in combustion, carbons, tobacco smoke. Most of these things are carcinogenic. And here's the one that's probably been studied in your liver. Your liver says, how do I deal with this? And there's an enzyme and it forms an epoxide. So aren't you glad you know all about epoxides? What do epoxides do? Well, they can undergo a ring opening reaction. So here is a base on a strand of DNA, reacts with that epoxide group. Now you have a piece of DNA that has this big hydrophobic group on it. That DNA is not going to be able to fold and do what it's supposed to do. What does DNA do anyway? It just holds information. It's the RNA that makes proteins. But I imagine a piece of DNA that has one of these on it, instead of making the piece of RNA it's supposed to, it makes some rogue piece of RNA. And what's that rogue piece of RNA do? Make rogue proteins, and you become a mutant monster. Well, you have a mutant monster that's a tumor that grows in your body, and the irony, you can't kill cancer, so it kills you. All right, on to something we want to know for quizzes and exams. Common names of benzene derivatives. Here's phenol, talked about that. Probably talked about styrene a little bit. Definitely have talked about benzoic acid. We've recrystallized it. So common name, phenol. You can buy toluene at the hardware store. I doubt they sell any aniline. Here's anisole. Has anybody heard of anise? Like an herb? Licorice. Styrene, polystyrene. Might have heard of styrofoam, acetophenone, benzaldehyde, and benzoic acid. We've learned that aldehydes can get oxidized to acids, di-substituted benzenes. You might have been exposed to these words a little bit: para, meta, and ortho. What does ortho mean? When y here is adjacent to x, we can call that 1, 2, or we can call it ortho. When we have a 1, 3 arrangement, we can call that meta. Directly across, we call para. So we can name this 1, 2 dichlorobenzene. Many times it will be called ortho dichlorobenzene. This one here would be called meta. Metachloral peroxybenzoic acid. Might have saw this in the epoxide chapter using a per acid. So numbers can be used to identify the relationship of the groups. Ortho is 1 and 2, disubstituted. Meta is 1 and 3, and para is 1 and 4. Now we have 3 or more substituents. Use the smallest possible numbers, but the carbon with a functional group is number 1. So I don't think there's any wrong way to number it. You give one of these 1, you're always going to have 1, 3, 5. Trinitrobenzene. All right, so I said you'll want to know these names like phenol, toluene, benzaldehyde, benzoic acid. Because notice this thing here gets named as a what? Gets named as a phenol. So this is going to be number 1 carbon, 2, 3, 4. So this is 2,4-dinitrophenol. And here you recognize the carboxylic acid group. We got benzoic acid here. So this becomes 3, 5. 1, 2, 3, 4, 5. 3, 5 dihydroxybenzoic acid. So here's some common names: M-xylene, paracreosol. This is the stuff they soak railroad ties in, or soak the bottom of a telephone pole in. All right, Phenyl indicates the benzene ring attachment. So maybe a long time ago when we had a hydrocarbon chain and one of these stuck to it, we could call it phenyl substituent. This thing here would be a benzyl substituent. And so we have benzyl bromide, benzyl alcohol. So here are two alky groups to know. Melting points, more symmetrical than corresponding alkane. So they pack better in crystals. So benzene has a higher melting point than, say, cyclohexene that can move around a little bit, or just hexene. Boiling points dependent on dipole moment. So para, let me just draw something that's para. I was gonna quit early so I could have a lunch, and then I screwed up and went to the second set of slides. So notice this is symmetric and it's not gonna have as big as dipole as something like this. See these two electronegative groups making this all lopsided. This is gonna have more of a overall dipole in that direction, where here, you know, there's some polarization that way, some polarization going this way. So that's why the ortho has a higher boiling point than, say, the meta. Density, these will still float on top of an aqueous layer, but they're more dense than non-aromatic due to that flat planarness most of them have. Generally insoluble in water, just like all hydrocarbons. So IR spectroscopy, got double bonds, carbon-carbon double bonds. You're going to see a carbon-hydrogen stretch that's just above 3,000. This was at 1,600. There was a quiz where you had a phenyl ring on there, and that was pretty prominent. NMR, I said between 7 and 8, you see some peaks, probably an aromatic ring. Carbon-13, a lot of chemical shift, similar to alkene carbons. Now, one thing we did go over is if you cleave this, make this a carbocation, you can draw resonance structures around that whole thing. So a benzylic carbocation is very stable, so stable that gives you the base peak here. So here's N-butyl benzene, UV spectroscopy. So the visible light spectrum ends around 400. That violet light that's hard to see, but these double bonds, you have electronic transitions from bonding and anti-bonding orbitals. And so a lot of these things can be measured using Beer's law, concentration. That's what we use UV spectroscopy for, not so much figuring out functional groups. What might be interesting here is seeing a shift. So we saw that benzene was special, that it's like unreactive. That's a characteristic of being aromatic, and unreactive in the sense of other normal things that have double bonds. But there is this mode of reaction for benzene. It's called electrophilic aromatic substitution, EAS, abbreviated for short. And so what happens? We have an electrophile, some species that has a positive charge. The benzene ring has all this rich electron area. And if that grabs a hold of an electrophile, we get this thing called a sigma complex. Now we have something that looks like an sp3 hybridized carbons. We've temporarily made this thing not aromatic, and a base can come by and pull off that hydrogen. Those jump back down and you get your third double bond in the ring back, and we see a substitution reaction occurring. So they're below and above the ring, and they are available to attack a strong electrophile to give a carbocation. Where's the carbocation? I think the carbocation, we'll see it in a better slide with the mechanism. Now this thing is resonance stabilized. The carbocation is either on that carbon or that carbon. Can't tell where the double bonds are. but then they can move around through resonance and stabilize this intermediate. And it's called a sigma complex because the electrophile is joined to the benzene by a new sigma bond. And as soon as we lose this proton, aromaticity is regained. All right, so now we can see a double bond rich in pi electrons. They grab this electrophile. So now all of a sudden, on a carbon adjacent, since we stuck it on this one, this carbon here now just has 3 bonds. It's a carbocation. You can use your resonance arrows, draw that moving over there, puts the positive charge there. Those electrons can jump down there, puts the positive charge there. So this thing is a sigma complex, stabilized by resonance, and then a base comes by, grabs the proton. Those electrons jump back down, and now we see a complete substitution. Electrophilic aromatic substitution. So at the beginning of our last chapter, we're now into the next chapter. We said something special is going on with benzene. We don't observe this reaction, which normal alkenes, we observe bromination readily. And then the slide said if we use the spheric bromide catalyst, this reaction occurs. And we get a substitution, not an addition. Just recall, this is an addition reaction. Here we have a substitution. So what is the electrophile? So here's Br2, here's our ferric bromide. Metals have a bunch of d orbitals everywhere. Those insert, you get this intermediate. And so here's the electrophile. A stronger electrophile than this thing by itself. So we're going to look at a bunch of reactions, and the first step is forming the electrophile, or we say it becomes activated. A strong Lewis catalyst, such as ferric bromide, can be used. So this positive thing collides with benzene ring. Those electrons grab that bromine. Those jump over there. Here's our sigma complex. Notice over here we have FeBr4, and it's got to have that negative charge. That's our base here. Now when it grabs a proton, it eliminates a bromine here. So notice now we have our catalyst is regenerated. It's always fulfilling to, a catalyst makes a reaction occur, plays a role, but comes out of the reaction unscathed. You get your catalyst back. So it's nice to see the ferric bromide there. Electrophilic attack, formation of the sigma complex, and then loss of a proton. Get your double bond back.